for the AP test. First, 3 more things about array lists. Everybody, please stop coding. Just look up here. I'll be done in 5 minutes. 3 quirks about array lists. We talked about linear searches last class. The AP Classroom and the AP materials, they might call it a sequential search. It's the same thing. Just didn't want you to get freaked out, right? Linear means in a line. Sequential means in a row, in order. So it's the same thing. Secondly, when you create an array list, it's possible to leave the type off of the right-hand side. See this line? Instead of putting string in both places, you can not put it there. But I'm requiring that you do put it there. So go ahead and see if I'll take points off, because I will. It's because REPL will say you're doing it wrong when you do it. Like just do it right. But it's kind of weird. The AP Classroom has one of the multiple choice problems. Does it this way? And so I'm showing it to you so you don't freak out. But don't do it. Don't do it this way. Always put the type on both sides, and everyone will be happy, particularly me. And then finally, I forgot to tell you earlier that when you use the remove method on an array list, it actually returns the removed item to you. It doesn't just delete it. It grabs it, deletes it, and then gives it to you. So look right here. If I say array list string names, and I add 2 names, and then I remove item 1, notice this remove is inside of a print, and it would print Elvis. Because when I remove that item, it hands it to me. Another example here, there's really 3 ways you could use that. You could totally ignore it, or you could print it, or you could store it in another variable. So right here, I created an array list. I put 3 things in it. I removed item 1 and stored it in a variable. And then I removed item 0 and just threw it away. I mean, you don't have to do something with it if you don't want to. And then finally, I removed item 0 again, and this time printed it. So line 5 stores the thing I removed in old name. Line 6 removes it, doesn't save it anywhere. Line 7 prints the thing that got removed. All 3 ways are fine. Any questions? Okay, sorting. There's 3 ways to sort that the AP Computer Science curriculum wants me to make sure you know. Today we're talking about 2 of them. The insertion sort and the selection sort. And yes, these things are going to be on the test on Friday. That's a week from today. All we're going to do Monday and Wednesday is practice, but you are going to have to put a little effort in to memorize what these 2 things are, because it's not necessarily intuitive. But you can do it. You have 7 days. Let's talk about the insertion sort. This is how it works. You start with the second item in the list, and then you go backwards all the way back to the beginning of the list and see if that second item should go anywhere earlier. And if it should, you insert it, bumping everything up. Then you go to the third item in the list, and you go all the way back to the beginning and see if that item should go anywhere, and if it should, insert it, bumping everything up. And hopefully you can see as you go farther and farther and farther, you're building a list that's perfectly sorted, but you have like a pointer where you're keeping track. Everything prior to this one is sorted, and then you move up another one, another one, another one. What would this look like in this class? You might be shown on the AP test a multiple choice problem where they showed you code. They didn't even say what it was, but they asked you to look at it and tell them how many times line 7 will execute or what gets printed or something. You're not going to be asked to code. You're not going to be asked to write this as code. And in fact, I give you the code and just showing you an insertion sort. But I want you to look at this 5261. We're going to do, this is the sort of question you might get on the AP test. What will this array list look like after 3 passes of an insertion sort? So remember, pass 1, we start at the 2, start at the second item, and you look backwards and say, should this go anywhere earlier? Yeah, okay. We insert it and everything bumps over. All right, so I'm saying what we did. Next, we're going to look at the 6. And we'll say, hey, should this go anywhere earlier? And no, it shouldn't. It's already in the right place. And sometimes nothing changes. That doesn't mean it didn't try. Like the computer can't just say, oh, I don't have to do this one because nothing's going to change. I mean, how would it know? It has to look and say, okay, am I going to have to change something? Next pass, it's going to be looking at the 1, and it's going to say, should this 1 go anywhere earlier? Obviously it should. So the third pass is it move the 1. So this little 4-item data set, we got perfectly sorted in 3 passes. And you'll have this in your slide deck. This is an insertion sort algorithm. I got it right out of the AP classroom, the multiple choice problems. We're going to walk through this code briefly using 10.8.3.4. And if we call this method with nums, this array, 10.8.3.4 is what it starts. And then this came right out of a multiple choice problem because they had this line 10 thing here. Let's look at what's happening. When you call it, it makes a for loop starting at item 1, going all the way to the end. Remember, item 1 is the second item. That's what I told you. It starts at the second item and then looks back to see if things should go back. And it sets a temp value to the current value. That's the one it's going to move. And then they did a while loop while the index is greater than 0 and temp, this current temporary item, is less than the previous one. Then we keep going back until we don't anymore. And anyway, you're gonna have to look at it more closely. I can't verbalize it, but you'll have that to look at. Again, you don't have to code it. You could copy that code right out and you could put it somewhere and you could add some print calls and try to see how it works. I don't want to spend probably the time required right now. So this sort method is relatively easy to code and it's quick for small data sets and it's inefficient for large data sets. Think about it. If you had 1 million items, it's literally going to look at 1 million minus 1 items and make sure that each one, by going backwards, is it in the right place? So when you get to like the 900,000th item and it was like a really low number, it might have to go through 900,000 items to put it in the right place. So these things, it could take longer and longer and longer. But for a small data set, even thousands of items, boom, done. But huge data sets, probably not a great way to sort. Second and last method of sorting is the selection sort. This one is a little different. You start at the very first item and you find, while keeping your finger, let's say, on that first item, you go through the whole array or array list and find the smallest item in the whole list. And you swap it with the first item. And then you go to the second item. And you look from there all the way to the end, find the smallest item in the list, and swap it with the one you're on. And so on. So sometimes it'll work out perfectly, but sometimes you're swapping over and over and over again. Sometimes things get moved all over the place. So let's take a look. I'm doing the famous Jenny, who can I turn to array, 8675309. We're starting at 8, and we're going to find the smallest number in the whole array, which is 0, right? And we're going to swap the 8 and the 0. Boom. Now we're going to look at the 6, and we're going only to the right. What's the smallest number? Yep. We're going to swap the 6 and the 3. So see, the 6 and the 3 got swapped. Then we're looking at the 7. We're going all the way to the right. What's the smallest number? The 5. So then we're going to look at the 7 all the way. It's going to swap with the 6. And then we're going to look at the 7 now, and we'll find the smallest number, which is itself. But it's not going to do anything. It's not, 7, 8, and 9. It's not going to swap it with itself. I mean, it could. It's not going to hurt anything. But it does have to keep looking. It can't just go, oh, I'm done. I can bail. That's like computers can't just look and go, oh, we're fine. Here is a selection sort implemented with an array as opposed to an array list. We're starting at 0, going all the way to the second to the last element. We're marking where the smallest item is. We're saying, hey, we're going to assume the smallest is the one we're on. We go through the whole thing and see if we find a smaller number. And if we do, we that's our new smallest one. And then finally at the end here, it's saying, hey, if I found something other than the one I'm on, then I do a swap. It's replacing. It has a temp variable and moves them. And again, you can look at that at your own time. Same issues. This sort, same issues as the other one. Relatively easy to code. I mean, look, it fits on one little page, and it's fast for small data sets, and it gets very inefficient for large data sets. Imagine if you had 1 million items and they were all out of order. Or if it was just 1 million down to 1 in the wrong order, every single time it would swap things, which would be crazy. Yes?
Would a large data set use that would be efficient then? Because it seems like everything would be efficient at that point. Like a large data set.
I'm blanking on the name. The question was, what would be a better sort algorithm for a large data set? And I'm which one? I couldn't hear you still, but there's I'll look it up. I'll look it up and tell you in a sec. I forget the name, but it's the it's called a merge sort. That is it uses recursive functions to recursive methods to chop it up in a different way. So, all right, let's practice, everybody. If I asked you this, what would this look like after 3 passes of an insertion sort? Remember, insertion is the one that starts on the second item and then looks backwards to see, should I be going backwards? So 6. Does 6 need to go before 8? Yeah, so the first pass, 6 goes 8. Now we're looking at 7. Should 7 go somewhere earlier? Yep. 7 gets inserted before the 8, bumping the 8 over. 9, no. So, and I just asked for 4 passes. This is 3 passes. Finally, we're on the 3. And yeah, that would go back to the very beginning. So this 4 passes, perfectly sorted. We're all done. And selection sort. What would this look like after 4 passes of a selection sort? So somebody tell me what the first step is. Go ahead.
Find the smallest number.
We kind of got our finger on the 8, and then we're going to find the smallest number, which is a 3. And then what do? Swap the 3 and the 8. So 3 and the 8, that's pass 1. Somebody else. Marcus, what's the next? Got our finger on the 6. What? You just do it?
There's nothing smaller than the 6.
Okay, but logically what we're doing is looking at the 6 and then seeing if there's anything smaller than a 6.
Yeah, there's nothing.
Yeah, I wanted you to say it out loud. There's no change. Same with the 7, right? Now we're on the 9. There is an 8. We're going to swap the 8 and the 9. So that's 4 passes. All right, here's a recap of what I need you to get done today. The warm-up, there's a Google form practice that's mostly about sorting. Then there's a practice REPL that probably doesn't have anything to do about sorting. I don't remember. And then there's a word group sentences REPL. Hey, I was also going to assign, because it was a block period before, the multiple choice questions for Unit 7. There's 18 of them. And they did get assigned in the AP Classroom, but you don't have to do them right now. We'll do them another time. So if you get an email from AP Classroom saying you owe me this, don't do it unless you are feeling particularly ambitious. I mean, I'm going to have you do it someday, but not over the weekend. I'm aware that we've got power and flooding issues.